Liz Fong-Jones, and I'm the Principal Developer Advocate at Honeycomb.io. And I've been doing Advent of Code every year since 2015, and I believe this is my fourth year of streaming Advent of Code. So I am going to kind of do stream chat, question and answer for the next couple of minutes, and then at 30 past, we'll go ahead and dive into some things I found useful during previous Advent of Code years that really are things that pop up every year that are useful to learn. Hey Eric, what is up? I am mostly just hanging out in my very tiny apartment in Vancouver, BC. I just moved about 3 months ago. So I'm hanging out here. As you can tell, it's not the ideal streaming setup, but this is where I work. And so sometimes you'll see me in this region. Sometimes you'll see me at a other desk that I use sometimes to get a little bit more peace and quiet. Depends whether my spouse is doing dishes or doing something or in the background. Are you excited, Eric? I bet you must be excited. Yeah, I've got two desks. Let me see if I can share this. So over here, this is my primary work PC. So it's a fairly well set up machine, in need of a couple of little hardware upgrades. Like this thing's like 5 years old. And then I also have a ARM64 machine that is also located at this desk, which is a Cortex 72 machine. It's the Honeycomb ITX I've streamed about before. And also upstairs, I think I can't choose screen fetch from that because it actually is configured to not take SSH, I think. Let's see. Do I have this? Yeah, it's not configured to accept SSH. But upstairs, I've got a tiny machine that has no graphics card, but it does have a Ryzen 4750G. So it's plenty capable. It's my fits into small spaces machine that I use for kind of podcast recording work and other stuff that needs to have absolutely zero background noise. So I'm actually moving in January. I'm pretty excited about that. And I'm going to have a dedicated room like that I can close the door on to do streaming or podcasting stuff. But unfortunately, that is not going to be until January. So for all of December, I'm going to be doing this either here or upstairs in the stairwell. This compromise that we have to make. Whew, yeah, I can imagine the blood pressure of having a big launch day. Yeah, I was on call over Thanksgiving, and yeah, it turns out that it's a little bit stressful when you have customers that depend upon you to make sure their services stay running. Cool. So let me just reset this real fast. Let me just also quickly make sure that I can go straight up to 00 on the hour and then dive immediately into the puzzle. Yep, okay. I've got my starter template code ready to go. So, some of you may be wondering, if you're here for the first time, what is Advent of Code? Advent of Code is a set of 25 problems, each with 2 subproblems that release every day in December. They're written by Eric Westel, who's in the chat right now. And we're counting down to 30 minutes until the first unlock of 2020. But if you look at the kind of previous events, you can see that they run all the way back to 2015. So this is year number 6 for me. 100%ed it every year. I don't expect this year to be different than 100%, but it may take a varying amount of time to get these done. The difference between part 1 and part 2, that's an excellent question. So let's go back to a previous year. And let's have a look at what the kind of difference between part 1 and part 2 might be. So if I go to Advent of Code, 2019 again. So if I look at this problem, for instance, it gives you a first subproblem to do. And then after that, they give you, Eric has a second half of the problem that builds on whatever you did for the first part of the problem. Sometimes it's a slight tweak. Sometimes it's a more substantial modification. Let's see, this one might be more representative there. So for instance, here, they give you a negative number. They just have you treat negative numbers naively at first. And then they're like, oops, actually negatives should be treated as 0, right? So you have to modify your code. So yeah, that's admin of code. All right, I've now filled enough time that it is 30 past, so let's go ahead and get started with the computer science overview of useful things you should know to do admin of code, even if you are not necessarily someone with a computer science background. Don't be afraid, actually. I've been a ops person for my entire career, for 15 plus years. I only got my CS degree in 2014. So these are things that, they teach you in CS school, but they also teach you a lot of other things. It turns out that for the purposes of admin of code, the first thing that you should really think about is memoizing. So what is memoizing? Memoizing is a fancy mechanism just for saying caching. It's a way of avoiding doing repeated work. So this example here that I'm showing you is from admin of code day 24 of 2016. And in this puzzle, you are asked to basically compute some things involving a maze, to compute the distances that would take to get between varying points in a maze. Oh yes, thank you, Ariel. It's not memorizing, it's memoizing. I know, those fancy computer science people. So you could, repeatedly compute the distance between every 2 points every single time you have to go through. Or you could store something that records the distance between any 2 valid points. And that way, as soon as you hit a point that you already know about, then you know that your distance to your target is just going to be, the distance you've traveled so far, plus the previously computed value. So one way of thinking about this, for instance, is something like that I tend to use a lot in my examples, called like the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, 13, and so forth, right? Where I could say, in order to compute the 15th Fibonacci number, I'm going to need to compute Fibonacci number 14 and 13. And then to compute Fibonacci number 14, I need to compute Fibonacci number 12 and 13. Wait a second, 13's there again, right? Like, I could compute Fibonacci of 13 every single time, or I could just store that to a table somewhere and just say, you know what, I'm storing all the values I've seen so far. Then the first time I encounter it, then I store it. And then afterwards, I can just read out the value that I pre-computed. So generally, when you memorize, you're typically doing a memorization across some kind of object or state for which you're storing some kind of value. So this leads you pretty neatly into needing a hash map or hash table of some kind, depending upon your language. And yes, it's precisely a CPU versus RAM trade-off. So you generally want to memorize things that are going to be expensive to recompute, but relatively cheap to store. And yeah, basically, if you are using a fairly modern language like Go or C++, you're in pretty good shape. There are pretty good hash map or hash table or map classes. So just make sure you understand how are you initiating a map. However, if you are using a language like vanilla C, I'm sorry, you're going to have to write your own hash map implementation. That I cannot really help you with because I've forgotten how to do it. It was a very long time ago. Okay, but one interesting property of hash maps that I'm going to point out is that hash maps depend upon not necessarily storing the values of the hash map kind of all in order, but instead you need to take the key of your hash and somehow be able to look up its position in this hash map or hash table. And often, if you have a sufficiently large and complex and unwieldy object, there's going to be a lot of kind of parsing all the fields in your object to figure out what went where, has anything changed in the object to make sure that 2 objects are either exactly equal or not. And that can be very, very computation expensive. So one trick that is useful, I haven't had to use it often, but it's a useful thing to know about that's happening under the hood, is that if you do not want your language runtime to be computing, hey, what is the value in pair position 1, pair position 2, then you need to provide a method of computing the hash to your hash implementation. So one way of doing this is if you have a bunch of things that can move around a grid or similar, you want to assign each piece some kind of unique value and combine the piece's value with its position. And then you can construct a board basically by saying, okay, I'm putting this piece into one place, so I'm going to XOR into the hash something that corresponds to the piece and its position. If you move the piece, you XOR the piece again, which removes it from the hash, and then you XOR it into place in the next position that it's in. And that means that updates are incremental, right? They're going to be incremental and order the number of pieces that you moved, and not order the total size of your board or the total number of pieces. So this really, really helps if you have something like a chessboard. That's kind of a classical thing that you see the literature on, is Zobrist hashes are often used on chessboards where you want to store a bunch of board states that you've seen before, but you don't necessarily want to store the entire board state. You just want to remember, I was there before. Okay. So you probably, hopefully, don't have to use a Zobrist hash unless you're using an esoteric language like C, where the language runtime's hashing function is not smart. Okay, technique number 3 that's helpful to know about. This is what was I doing here? Yes. So this is what was I aiming to teach here? I think I was aiming to teach A-star search. Yes. Okay. Technique 1 was memoization and hash maps. Technique 2 was more efficient hashing for storing your board states into your hash map that you're using to memoize. Technique number 3 is the A-star search. So A-star search is a form of breadth-first search. So let's first start with our searches. There's kind of depth-first and breadth-first searches. So depth-first means that I start exploring from a point, I go to the next point, I go to the next point, and so on and so forth until I hit a dead end, and then I kind of backtrack and go back one step and then try to go forward to as many places as I can, which is potentially useful if you're trying to get somewhere fast. But the instant you start running into dead ends, you're going to find that that your algorithm really, really slows down and starts consuming gobs and gobs and gobs of memory. If you're doing a depth first search. So the more common technique that people tend to use to kind of explore an unknown space, like exploring a maze, is a breadth first search. So in a breadth first search, you start at a given place and you just notice, where are the possible places that I can go? Once you've noted down the possible places that you can go, then you repeat this and say, okay, now I'm going to explore each next possible place I can go, but instead of immediately chaining off of that next place, I'm just going to write down the neighbors of the next place that I went. So A prime, B prime, C prime, D prime, right? And then instead of going to A double prime, you would then go, check and see who are A prime's neighbors, which might be A double prime, A prime B, A prime C, and so forth, right? So you're kind of building up, how many places can I get after one move? How many places can I get to after 2 moves? How many places can I get to after 3 moves? And the critical piece is that you don't visit any of the places that are reachable after 3 moves until you've exhausted all the places that are reachable after 2 moves. No, day 1 question will be out in 20 minutes. This is just a really quick summarization of useful computer science tricks to put in your knapsack. So A star is a breadth first search where you have a little bit of a heuristic that helps you. A heuristic is kind of like a hint. A star search is a heuristic where you're not only searching breadth first, you're also doing the search informed by some useful property. For instance, if I know the coordinate that's the finish of the maze, and I know where I'm currently at, I know that it's going to take me, at least 5 moves or 10 moves or whatever to get there. However, if I start moving backwards, then I'm going to find that heuristic gets longer and longer and longer, right? So I don't necessarily want to explore away from my objective first, right? I want to start exploring towards my objective if I possibly can. I want to always be exploring to minimize the distance between, the naive distance between me and my target. So that's essentially what we're doing in here, where we are constructing a work list that is not just ordered by the total distance I've traveled so far. It's also had a number added to it, which is the minimum number of steps that I need to take to get to my destination after the current number of steps I've taken so far. So it's a handy trick, and I believe that A9 just linked a awesome resource to it that helps you better understand it. So just like know that term, A star, and know to go looking around for it anytime you have a I'm exploring a maze type of situation where you don't know exactly how to get there, but you kind of have a rough idea of whether you're warm or cold or hot. So that is technique number 3. Oh, good. I'm doing good on time. I've got 6 techniques to tell you today, and we're 10 minutes in, and I've done 3 of them. Cool. Okay. Technique number 4. Technique number 4 is a futility abort. It's a futility prune. So the idea is, let's suppose that you're exploring that maze, and you've already gotten to your destination. If you've already gotten to your destination, you don't need to do any of that other work, right? You know, you might have found an inefficient path to your destination, but if you're looking for the shortest path from A to B, and you found a route that is 27 steps, anything that's taken over 27 steps, you can be like, you know what, we're not exploring that anymore. Like, we know of at least one thing that is shorter than that is 27 steps or shorter. So this is a useful technique if you're, for instance, not doing A star, and instead you're doing like a depth first search, or you're doing a parallelized search where you have more than one worker computing in parallel, where someone may have beaten you to a more efficient solution, and therefore, if you are working on something that's less efficient than the current best known solution, you need to stop doing work. You need to stop forking off new work at least, and if you are about to start new work, just stop. So this general kind of technique is called pruning because it's kind of like, you know, you're picking what to do next, so it's almost like a decision tree. So pruning just means like we're going to snip off those branches of the tree because we don't need them. We know that there's something else better out there. So yeah, as you can see here, right, like this is a common technique that we use when we're saying, you know what, I'm going to fork off new work and I'm just going to let Go's scheduler handle deciding when to run it. So normally this can be slightly more efficient with a star search where you're just explicitly populating the priority of the queue and what you read off the queue. But it can be useful if you decide you want to go with parallel computation to either say, you know what, like this is not futile, let's go ahead and spawn off a new worker to check this scenario, or we've seen this already, like we know that we have something better, don't bother further adding to our computation workload. So that's item number 4. Okay, technique number 5 you should know about. How to simulate things moving, or things like, or a world state that is evolving over time. So this is kind of the prototypical example of this. This is 2017 day 20, where you're asked to simulate over 1,000 cycles, having a bunch of particles, each of which has a position, velocity, and acceleration. And you're just asked, you know, what are the positions of the particles going to be in 1,000 turns? So this is where it really starts to matter to think about things like, how am I representing each particle, right? What are the properties? Am I representing its position, velocity, and acceleration? How am I representing each of these things? And can I potentially optimize things by creating an operation to add 2 coordinates together, for instance? So here we define for a universe in 3 dimensions, there's a XYZ vector, and there's a vector for each of position, velocity, and acceleration. And then after that, we kind of have the notion of board state, which represents what does the world look like after some number of ticks in time. So once you have something like that, then you want to create a function called tick that basically updates for one timestamp. And that timestamp might do something like, check whether to remove objects or to modify their state, and then advance them forward by applying the velocity transformation. So for instance, where did I do this? So we say that that velocity is velocity plus acceleration, or position is position plus position from the previous tick plus velocity. So that's a very, very common thing that Eric tends to ask you to do. Not all of them are this simple. He gets really, really fiendish, and he's done previous things that are literally like simulate NetHack, right? Simulate your character in battle against an opponent moving around a board, right? But the fundamentals are still the same, right? The fundamentals are represent your world state, represent each actor in the state, and then have functions that decide what is the actor doing on each turn. As long as you can do that, you kind of are conceptually familiar with the tools that you'll need, even if, like me, you might struggle a little bit with the reading comprehension of what does it really mean to tick a board state or to tick an individual actor. So that's technique number 5. Finally, we come to technique number 6, which is the most common one, which has been represented, I believe, in the past 3 or 4 advents of code in a row, which is representing, thank you for the cheer, large data bank. So technique number 6 is representing a processor in a computer by simulating the behavior of the processor. So if you're not familiar how a processor works, don't worry too much. I'm going to walk you through it in 10 minutes, so you have at least a basic idea of how to approach this. In general, a processor is a sophisticated version of that board state machine earlier, except for instead of simulating what's happening to particles, you're simulating instructions that are being run that affect what variables or values are present in what we call registers. So this is what a board state might look like if you are running a virtual machine. A virtual machine has something that we call an instruction pointer, which is which instruction am I currently executing. It has a list of instructions that it could potentially execute. And then it's got some amount of registers, each of which has a name and has a value stored in it. So in order to tick the machine one step, you look at the instruction that's located at the position specified by the instruction pointer. So if the instruction pointer is 5, you look up the 5th element in your instruction array. And then you do whatever that instruction says. So that instruction might be something like subtract A from B. Or an instruction might be set the value in register A to 5. So you will want to understand how to use, for instance, a lambda function in order to make your job slightly easier. But if you don't know how to do that, that's perfectly okay. You can hard code the logic, right? Basically what it says is, I am going to, if I'm asked to tick the machine, look up the instruction at that position and perform whatever the instruction says, which will possibly involve modifying the value of a register, or even last year, we had self-modifying code that would modify the instructions that would be run in the future. So that's a little bit more sophisticated than you'll necessarily have to do right off the bat, and Eric has done in the past a very good job of walking you up to the level of difficulty of having self-modifying code. But kind of the initial basic steps are be able to represent your current instruction pointer, which index you're at, being able to represent the list of instructions you're going to be asked to potentially run, and then have it keeping track of your registers. As long as you can do those things. Oh, and by the way, at the end of each instruction, typically you increment the instruction pointer, right? So you're typically walking through step by step by step by step, except for sometimes you'll modify the instruction pointer to either skip over some instructions or jump backwards, and that's what makes it like a full-functioned computer, right? That is Turing complete, and not just this is something that's always going to return the same input no matter which values it's given. Yeah, in code last year was pretty fun. So those are really the 6 foundational techniques. that I suggest that you at least know the names of, so you can look up in a little bit more depth when you actually encounter these concepts out in the wild. So to review. Concept 1, memoization. Keep a giant honking hash map, populate it with the kind of previously computed, populate it with kind of the input to the function and what its previous output was, so you don't repeat computation. So the code that I'm showing you is 2016 day 24. Second technique that I mentioned is be efficient about your hashing. So make it easy to compare whether you've seen a previous state and a current state. So this means you might need to do something involving adding a easier hash computation function that doesn't involve iterating through the entire object. Third technique is doing an A-star search, so exploring with a heuristic that helps you prioritize the things that get you closer to your target first until those things potentially dead end and you have to rewind. Technique number 4 is stop doing work if doing that work is not going to improve your result. Technique number 5 is doing physics simulations or any kind of simulation tick by tick by tick. And then technique number 6 is understanding how to build a simulated instruction set. So how to keep track of registers and instruction pointers and instructions. And yeah, Ariel's linking the int code compendium, which is now apparently an esoteric language. Congratulations, I guess it's graduated. All right, so I've been talking for a little while. I'm happy to take questions while I take a drink of water. And other than that, we'll go ahead and get ready for the last 7 minutes of this countdown. How many of you are doing Advent of Code for the first time, or like heard of Advent of Code for the first time? How hype am I? I'm pretty hype. I admit I was up at 4 a.m. this morning to do an Eve thing, so I'm a little bit more tamped down than I otherwise would be about the first day of Advent of Code. But I'm doing pretty good. Yay! Welcome to our community, Arendon. You may want to become familiar with the Advent of Code Reddit. It's where a lot of folks hang out. Yeah, 12 a.m. problem drop is really rough for East Coasters. I did the last couple of days of Advent of Code on Eastern Time and was up at midnight and often until 3 a.m. Now I'm on West Coast time, which is a lot easier for me. I also did some of last year from Australia. And fortunately, none of us are traveling anymore. It's 2020. What do I do when I get really, really stuck? Eventually, I will potentially ask viewers for hints or ask my spouse for hints. My spouse has a little bit different background than I do. She comes from a kind of programming languages, computer science, more formal computer science background, and so she often knows a lot of tricks that I don't. And she also minored in math, whereas I didn't. So ask my spouse is usually kind of my first lifeline. Other than that, the Advent of Code wiki does have some good. The Advent of Code Reddit has often some hint posts that can be pretty helpful. But in general, like, because I do every solve streamed, I try not to cheat initially, and then, I'll ask for hints from my viewers as I get more and more desperate. It usually doesn't get that bad, though. Because I have, this is my 6th year doing it. Like, I've seen a lot of the tricks that Eric likes to pull. The only one that threw me last year was the one that involved discrete math, which was a little bit beyond my capability. But I wound up asking my spouse for help there. Yeah, doing it in real time is fun, but do not feel pressure to do it in real time, right? Like, I'm doing this to educate and inform people. I'm not doing this, because I want to get first on the leaderboard. Like, honestly, in the first 5 to 10 days, I typically finish in the top 500 or so. Like, I'm not aiming for top 100 because, like, I aim to educate along the way, to write readable code, to explain what I'm doing. And that will slow me down compared to the people who have, like, fancy macros, who are, like, typing super fast. I don't really do that. I find I start clawing back and catching up by days 10 to 15. I tend to place in the top 200 to 300 on days 10 to 15, because by then there's enough complexity that it really matters, and that it actually is a competitive advantage for me to be able to explain out loud and kind of have this virtual rubber duck audience. Thank you all. So that kind of helps me make progress, where it stops being about how fast can you brute code to reach the top 100, and much more, do you have a good understanding of the problem? Have you thought through which algorithm to use? Right? Are you able to effectively debug your code? So that's kind of how I tend to approach it. But don't feel any pressure to do it right as it drops. It's okay to watch a replay of this. You don't have to watch this in real time. And when you're solving it on your own, again, don't feel pressure to do it in real time. I think there is a degree of motivation of trying to finish in December at least, because otherwise, you could potentially go weeks without touching Advent of Code again if you don't kind of have that little motivation of I want to finish by December. But other than that, be flexible, and the puzzles will always be there, right? 2015 through 2020 are still up. Awesome. Have I read the AWS postmortem? Yes, I did read the retrospective. I mainly was reading it for impacts to my company and to our customers. I haven't kind of done that detailed analysis aside from oh my god, it's file descriptors again, right? Every sysadmin has the, oh god, it's DNS again, right? That instinct is yeah, there, but for the grace of God, go I. Oh, hey, Cal. Yeah, I think that for me as a developer advocate, this is how I keep my skills with kind of raw computer science fresh, and also to share my passion and for education with you all. This is kind of why I do it, is because otherwise I'd get more and more divorced from actually working on writing code every day. What structure do I find useful besides hash maps? Honestly, right, the struct and the hash map in Golang are pretty much mostly what I need. There are other things that are language properties are useful, right? Channels are useful, Go routines are useful, but those vary from language to language. Yeah, definitely rereading the problem is hugely helpful. What does a good SAP template look like? Well, actually, with 3 minutes to go, let's look at my template. So my template typically has a set of inputs. So I'll paste whatever output we get here into day one, inputs day one. And then I've got a function here that will basically, my template basically, everything starts off in the main function until otherwise described, and then I pull out bits of logic as I need. But the core loop basically is read day one's input, and then it will usually be some sequence of bytes, right? And then I just parse it by new line, and then transform each character, each set of numbers on a line to an integer, and then I'll do whatever work is required. So we'll see how well that works for me going into this year, but so far I found that this is my can't-fail template that I always start with, because I hate looking up the manual for file I/O. I just hate it. I just recycle this every year. Yeah, I guess, yeah, heaps can be useful. I just tend to use a personally. I just tend to use a Go slice, and that's good enough for me. Yeah, 1 minute to go. Well, I guess I'm going to run an ad. And for people watching this on YouTube, yeah, it's going to be slightly desynced by 5 seconds, but, whatever. I'm not aiming for the fastest in the world. This is mainly to spare people joining the stream or whatever from having to watch ads. The joys of advertising-populated platforms. And thank you for the sub, the real Storm Sweeper, although you may or may not see this depending on your Twitch Turbo subscription. Okay. So, in a second, we will be back. All right. Welcome back, folks. This is problem number 1. So, we're taking a vacation on a tropical island after saving Christmas 5 years in a row. Go me. It's cash only. Stars. Okay, now we know what the currency is. I need to pay the deposit on my room in order to enjoy my nice vacation by December 25th. Okay, so find the two entries that sum to 2020 and multiply those two numbers together. Great. That seems pretty straightforward. So it's just a... come on. Oh no. Is this my internet connection, or is this... I think this is the servers being overloaded. Exciting. Well, while I wait for that to resolve, let's go ahead and start writing the code that I'll need for this, because that seems feasible to do. So I need to keep one of these. So I'm going to make a int array. Poor Eric, hugups. Hugups to Eric, hugups A9. I'll be here, don't worry. I have enough information to proceed here. So let's go ahead and do this. So we'll populate this. And actually, yeah, that's fine. That'll be fine. Okay. So don't think I'll have any empty lines here. All right. Let us set split scene I equals n. All right, and we need the so. Okay. Just going to do this. If I is greater than or equal to j, then we just continue. So this is a standard mechanism here for doing a. So this is a standard mechanism here for doing a just a any combination of indexes I and j, where you try to avoid checking ints yourself and where you try to avoid double computing. All right. So if I is greater than j, then continue. So if I plus j equals 2020, then okay, I think this should do the trick. So let's go ahead and pass this in and verify that works. So we're just going to give it our sample input. Oops, make n and m. Oh, I don't actually need n and m yet, so that's fine. Oh, this is n and m here. Yep, this is a bunch of cherry browns. My partner Lydia convinced me to get this. Failed to parse, and then 514. Why did I fail to parse? Oh, I bet this is just the trailing new line, so I did need that code after all. Okay. Let's just do that. All right, that should do the trick. Yep. So that works. So now, assuming that this eventually comes back to life, I should be able to plug in my puzzle input and get started on part B. Thank you for the raid, Jacob. Okay. because I'm not in a rush to set any speed records, I'm just going to sit here and let the servers recover. I don't feel any immediate pressure to keep on refreshing this because, like, again, I'm not trying to place, at least not in the top 100. Like, it would be nice to place in the top 500, but, you know, it's fine. This is day one, and I'm more aiming to educate and inform and entertain than beat any records. Thank you for the sub, Fear of Code. And earlier, thank you for the sub A9. Thank you for the sub The Real Storm Sweeper. Really appreciate the support. Why am I not trimming? Yeah, it's a good point. The other thing I can do while I'm actually here, you know what, is I can just do... I think I can do this. Oh. I think that'll work too. Oops, I forget, does this work? Well, this is certainly going to work. This is where I refamiliarize myself with some of the odder operations in Go. Nope, that has to be, this is not Python. This trick works in Python, but it does not work in Golang. Grumble, grumble. Okay. Yep. Hug ops to Eric and crew. Oh wow, the entire server is down. Well, I am glad that I kept that open and didn't immediately refresh the puzzle as well, because that would have been a little bit sad. All right, folks. Well, thank you all for being here. May as well go ahead and take a moment while we're sitting here waiting to go ahead and plug my employer. So I work at a company called honeycomb.io, and we are a company that helps you understand bugs in your distributed systems. So for something like Advent of Code that's just running on a single computer, it's a little bit overkill. Oh, I hear it's up. There we go. All right, but for a more complex distributed system, honeycomb.io helps save you time and helps you understand what's going on in your system. Okay, so we have a result here, so I'm going to just feed this in. And I got rank 863, no surprise, because I was late refreshing, that's fine. If I can find 3 numbers that meet the same criteria. Okay, that's fine. So we're going to do this pattern. Except we're going to do this. Okay. And this means I don't need this part B flag here. I think that the complexity is fine here to iterate a 3rd time. I think that'll probably be okay. All right, so now we do part B, which I think just involves another one of these guys. And if it does blow up, then I will know why. Okay. So let's just do this, or K and O. Okay. Okay, I think this is going to be the answer. So I'll just go ahead and feed it in here. And I got rank 827. Yep, okay, that's straightforward enough. So we're just going to... I hate that Nano's developers recently took away the option just automatically run Go format. Okay. Let's see. That looks fine. So we're just going to go ahead and check this in. And let's go ahead and push it up to GitHub. So now let's talk about slightly more efficient ways of doing this, because in this particular case, there were only 200 inputs. So, you know, what, that's 200 times 200 divided by 2, or, right, so that's only like 200, right, 20,000 entries to scan over. If I multiply by another 200, right, and we're dividing by the factorial because we're doing choose combinatorics, then you get, you know, a number that is a little bit bigger, right? It's 66 times bigger, but it's not like, you know, that can't be right. Why am I confusing my choose math? It's not permute. Yeah, it's choose. Yeah, so it's, you know, it's some number larger, right? Like it's not 200 times larger. It's 66 times larger. But like, you can imagine if this were a larger n, it would be a little bit of a problem. So let's go ahead and refine this a little bit. So kind of the first thing that I might want to do here is I might want to probably avoid doing, probably want to not recompute I and j repeatedly, because I know what those results of I and j are. Okay, one easy optimization here. Let's look at the structure of this. None of these inputs are greater than 2020. But what we do know here is if n plus m is greater than 2020, because none of them are negative, if none of the numbers are negative, which I know they're not negative because I've looked at the input, in fact, are any of them 0 potentially? Let's just see. Nope, none of them are 0. So let's add an assertion here. So optimization invariant broken, s is less than or equal to 0. Okay. Great. Yeah, whatever, fine. Okay. So assuming that that's true, then if they're greater than or equal to 2020, we can immediately break. So let me just quickly demonstrate the savings here. So this previously took about 2.6 seconds, but I think I'm running a bunch of these loops too many times. I don't need to. So if I apply this optimization, oh, it's probably taking the time, most of the time is spent compiling. Ugh. Okay. So how do I avoid this problem? I guess I have to compile 2 different versions of the binary. This is actually, at this point, right, like, it's measuring something that really fundamentally doesn't matter that much on a problem of this size, but, you know, we're doing this for giggles at this point. Okay. Okay, yep, there we go, right, so n optimized, it takes about 5 milliseconds. So now let's n comment this. And now it takes a third the time. Dynamic programming, yeah, let's talk about dynamic programming and memoization. Again, like, this is not going to make a huge difference because the amount of computation we're saving is very tiny. We're only saving like a single addition here, but we may as well apply this trick here. So this is just to demonstrate what you would do to memoize, recognizing that it doesn't actually save us time in this case. So let's do this. So I am going to define a pair structure. So I've defined A and B in the pair. So I'm going to instantiate the memo here. And then what we do here is going to populate this. Memo of pair ij equals I plus j. That seems right. So again, you can see why this would be a preposterous thing to do for this specific problem. But in this case, we're finding this useful. Pair ij is n plus m. So now, because I know I've seen every valid combination of I and j from memoizing above, I can just use this without having to recompute it at each step, which is kind of useful. So now I have sum nm is memo pair ij, and then now I can use this here. And now I also don't have to recompute this here. So I've saved some number of additions, but I've introduced a hash access. Okay. Sum nm. Okay, so now if I time this, it should take... Whoa! That was not what I was expecting. I guess the answer is, yes, if the computation were more involved than n plus m, then it would be worth doing. But in this case, this is really not worth doing. I am going to do this though. I will get to that question in 1 second. That needs to be this. Okay. Okay, now we're back to it being nice and snappy. Ariel points out that yes, you could look for the remaining values. So let's talk about how to do that really fast. So if we were to do that instead, then instead of iterating over here, this would be a simple lookup. So yeah, let's do it this way. Okay, so I'm going to remove the memo because I don't think it's worth doing. But the one thing that is potentially worth doing here is, as Ariel points out, instead of this being an integer, this could instead be a hash, except for then it's not ordered. So I think we need something like this. So the way that we would approach this then is no, trying the memo did not break part B, I think. Oh, yeah, you're right. It didn't print. It's fascinating. The memo should have worked. I'm trusting that it was just a small mistake on my part. Let's see, where was I? Oh. The problem is... No, not here. Okay. As I was saying, the simple thing to check here, instead of running this inner loop, is we can just bypass this inner loop here. 2020 minus some nm. Then we have a winner. Something like that should do the trick, I think. N times m times 2020 minus nm. Oh, why am I calling it nm and not mn? Whatever, it's fine. Okay. Oh, and this needs this check here. See whether this runs first of all. Nope, I still have a broken part B. Grr. What's broken here? I bet it's not finding an answer. But that's my problem here. Let's see. Well, there's an easy... What did I do here? Let's get rid of my memo here, because I'm not memoizing anymore. Oh, duh. Break part B, that's fine. I'm adding n and m for the values here, that's correct. Add 2020 divided by... Oh, sorry, Lpens, I'm trying to understand what you're doing. Yeah, right now I'm working on trying to do Ariel's suggestion, which I think is also Lpen's suggestion to set it to look for the goal values. Right, like I think this is what I'm doing that avoids having to iterate over each one. So why is this not working? Because this was previously working. NMO, that's O. Is it that I'm this broken? Oh, that's the problem. That needs to be a continue, not a break there. This optimization was the one that was wrong. Okay. There we go. Now that's printing both answers. Why do I not need a... The sums of two entries... No, contains just has all of the previous values. So yes, you're correct that I could on the first... Right, I'm pretending that none of the work in part A happened. Right, this work here is almost the same work that happened here. Do I know that I don't have to use nano? Yes, I know this. I have been a nano user for I I have been a Nano user for 17 years. I am not changing. I also used to work for Chris Allegretta, who is the one of the creators of Nano. So no, I am not going to use any editor other than Nano. I'm deeply sorry to offend. Yeah. Okay. Well, anyways, the glaring problem with my previous memoization was literally that the break needed to be a continue here. But yeah. Okay. Let's do the thing that was suggested earlier, which is fine. Which is if we keep track of these values computed here. Wait, I'm a little bit confused why that actually is why it's actually a time savings to compute to pre-compute the sums any further than this n squared loop. You have to I think do the n squared loop. I don't think you can get away with shorter than n squared time. Oh, for part one, yeah. Part one, you're absolutely correct. Yeah. So let's just fix that up. That's completely fair. Yeah, I do not disagree. You're absolutely correct, Justin. So this could just literally be. Oh, thank you, Fear of Code. Thank you, Dashmath. Thank you, Pegasus. So you're absolutely correct that you're absolutely correct that this would be faster. Let's just make sure I didn't break my code. Thank you, Justin, for the tip. You're right. So that does right. Like I think fundamentally you can reduce the cardinality by a factor of that last ply. I don't think you can get out the cardinality one more degree. But yeah, let's just make sure I didn't break it. Okay, yep, that still yields the same result. It runs actually about in the same amount of time. But again, this is because the n count is not that large. Okay, I feel actually pretty happy with this. I'm just going to change... wait. Oh! That's why I was so confused. It's M and then N in the order. I swear I know how to use the alphabet. I swear. Okay. Okay. There we go. Okay, I'm going to consider this plenty fine for now. Cool. Let's go ahead and add this as the solution then. Do I like this? Fine. Yeah, it seems fine. Okay. Okay. And let's go ahead and push it up. Awesome. So I think that's going to wrap it up for here, folks. Fortunately, I only needed to run the stream past the unlock for half an hour. Some nights it'll be short like this. Other nights it'll be longer, and I'll just be wanting to get off the stream the instant I solve the puzzle because, like, if it's 3 hours later, I'm sorry, I'm not sticking around to optimize. But it was fun doing this with all of you. And go ahead and check out some of the other streamers. I will probably go ahead and send a raid over in the direction of. Let's see, is Anthony Codes streaming? Yeah, Anthony is streaming. Let's go ahead and raid him now that I've finished. Coincidentally, I believe he is... Which language is he using? Well, I guess we're about to find out. So I'm starting my raid, I'm stopping my stream.